Hey, welcome to this lesson on angle relationships in circles. You'll need a piece of paper and pencil to take down a few notes. You'll want to pause the video for this first slide. And slide 2. In this case, what we have here is a theorem, the inscribed angle theorem. And what you need to understand is that it really doesn't matter the cases over here. In case 1, what we have is one of the sides of this angle ABC going through the center of the circle. Here we have one side on either side of the center of the circle, and here both sides of the angle on the same side of the center of the circle. It doesn't matter any of those cases, the formula is still the same. This inscribed angle, the one where the vertex is actually on the circle, so angle B in all 3 of these cases, is going to be half of the intercepted arc, which is arc AC, the blue arc in all 3 cases. So whatever that arc measures, whatever arc AC measures, angle ABC, the inscribed angle, will be half of that. So let's use that idea in order to find the measure of angle PRU. Now, PRU is this angle right here. Okay, and what we should notice is that PRU is intercepting arc PU, which is this arc right here, all the way around. Back over here to finish that. Okay, so that's the arc that angle PRU is intercepting, this 118 degrees. Well, our rule says that this inscribed angle PRU is going to have to be half of its intercepted arc. So measure of angle PRU is half of arc PU, half of 118 is 59 degrees. Okay, now I want to find the measure of arc SP. So I'm trying to find the measure of this arc right here. Well, if I go back and look at the inscribed angle right here, it measures 27 degrees. And that has to be half of the intercepted arc. So angle SRP is half of arc SP, and 27 is half of 54 degrees. Okay. All right, now we want to find the measure of major arc ABC. So what we're talking about is the arc that goes from A all the way around to C, but has to pass through D. So all the way around here. That arc. That's the one we're looking at. And what we should see is that the angle that's intercepting that arc is the one created here at B, angle ABC. That's the one that's actually intercepting that arc. And we see that that angle measures 135 degrees. So since this is the inscribed angle and it has to be half of the intercepted arc, then I can think about just doubling this number. Doubling 135 is going to get me 270 degrees. But here's how it looks algebraically. Setting up the equation, and then again you have 135 degrees is equal to half of the measure of the major arc, so I'll double both sides to get 270 degrees. Now I want to find the measure of angle DAE. DAE is just this angle right here. So I want to find the measure of that angle. That's an inscribed angle, and its intercepted arc is arc DE, which measures 76 degrees. So I'm just going to take half of that. Half of 76 is 38 degrees. Okay, now what we have here is theorem 10.9, and basically what it's telling us is that I could have 100 inscribed angles here. But if they all intercept the same arc, so this red inscribed angle intercepts the gold arc here, AB, the blue inscribed angle intercepts the same golden arc, AB, and the green inscribed angle intercepts the same gold arc, AB. So all three of these inscribed angles, the red, the blue, and the green, intercept the same arc. If that's true, then all three of those angles have to be congruent to each other. So angle C, angle D, and angle E are all congruent angles. Okay? That's all that this theorem is really telling us. So we will use that to help us solve some algebraic problems. So here's an example. We're asked to find the measure of LJM. So let's make sure we understand what we're asking for here. That's this angle right here that I'm marking in purple. LJM, that little tiny angle. Well, what I should notice is that LJM, when I look at the sides of it, the JL and the JM, they come together to intercept arc LM. But this angle K up here, when I look at its sides, it also intercepts arc LM. So angle J and angle K intercept the same arc, LM. That means that those two angles have to be congruent to each other. So I will use a little bit of algebra and set these two pieces equal to each other. So 5b minus 7 equal to 3b. Subtract 3b from both sides and add 7. 2b equals 7, making b 3.5. Now I'm actually asked to find the measure, so you always look at the instructions. Find the measure of LJM. Well, LJM measures 5b minus 7. So what I need to do is plug the b back into that. So I end up with 10.5 degrees for the measure of that particular inscribed angle. All right, next theorem. Sometimes this theorem is a corollary of the inscribed angles theorem. Our book calls it a theorem, so we'll stick with that. So theorem 10.10 is saying that if I have an inscribed angle, which is what we have right here where this right angle is, if it's inscribing a semicircle, which this one is doing, so we're talking about half a circle is the intercepted arc. Well, we know that half a circle measures 180 degrees. And we are an inscribed angle intercepting that 180 degrees, and inscribed angles are half of their intercepted arc, and half of 180 degrees is 90, and that's why we have a right angle here. So if you are intercepting, if you have an inscribed angle intercepting a semicircle, your inscribed angle has to be a right angle. That's what this theorem is telling us. Okay, so using that very idea, I can see that angle Z here is actually intercepting a semicircle right here. So since it's intercepting a semicircle, this angle has to be a right angle. So all I have to do to solve for A is set 5A plus 20 equal to 90 degrees. Solve by subtracting 20 and then dividing by 5, and A is 14. Okay, so here what we're trying to do is find the measure of angle EDF. So let's make sure we're clear. We're trying to find this angle right here. And EDF is represented by the 2x plus 3. And we also know that EDF is intercepting arc EF here. And so what I can also see is that angle G here, angle EGF, is intercepting arc EF as well. So that tells me that angle D and angle G are going to be congruent to each other. So I'll set them equal. I'll subtract the 2x or sorry, add 2x over to the other side, subtract 3 to the right, having 4x equals 72, dividing by 4 gives me x is 18. Since it asked me for the measure of angle EDF, then I need to plug back into the 2x plus 3. So I get that the measure of angle EDF is 39 degrees. Alright, now this theorem is talking to us about a quadrilateral inside a circle where every vertex of the quadrilateral is on the circle. If you look for this in other locations, you may sometimes see it called a cyclic quadrilateral. That'd be CYCLIC, cyclic quadrilateral. But the idea here is that the opposite angles, so for example the two red angles here, A and C, are going to be supplementary to each other. Same thing for B and D, they're going to be supplementary. Here's the idea of why that's going to work. So if I look at the intercepted arcs, let's look at B and D and their intercepted arcs. So D is intercepting everything from A around to C. So I'm going to mark that. So from A all the way around to C. Okay? Now that's what D is intercepting. Now let's go look at what B is intercepting. Okay? Well, it ends at A and it ends at C, so it's going to be everything from A around to C in this direction. Okay? Well, when I put those two things together, there's no overlap. It's just the whole circle. And an entire circle measures 360 degrees. But these two angles that I'm talking about, angle D and angle B, which are not necessarily congruent. So don't get that. Don't think, oh, they have to be equal to each other. No. These are two different angles, but they are inscribing together the entire circle. And the entire circle is 360, and inscribed angles are half of that. So together, they should be half of 360, or 180 degrees. So they're supplementary to each other. So for D and B, they're going to add up to 180, and for A and C, same concept, they're going to add up to 180. Alright, so using that very idea, we're going to solve for the different angles here in GHJK. Well, what I'm going to do is I'm going to look at two opposite angles that I have information for. That would be G and J. And I'm going to know that those two angles have to be supplementary because what I have here is a cyclic quadrilateral. So I will set those two, their sums equal to 180. Solving for B after a little bit of simplification, I get that B is going to be 15. And so now I can actually plug back into each angle and get those measures. Now the only one I don't have anything for is H, but once I plug into J, K, and G, it's fairly easy. Once I know what those three angles are, I'm dealing with a quadrilateral here, and the sum of the four angles in a quadrilateral is always 360 degrees. So I can just take 360 minus these other three angles to get H. So plugging in, G, J, and K, again, it's fairly easy. I just plug into what I had. So for example, G was 3B plus 25, so 3 times my 15 that I got for B plus 25 is 70 degrees. And you can see how to do J and K the same way. And then I can just either add all three of these together and subtract from 360, or as it's showing here, realizing that K and H, because they're opposite angles in a cyclic quadrilateral, have to sum to 180 degrees. Okay? And so adding those together equals 180. Either way, I'm going to get that H is 99 degrees. Alright? Now, this theorem is for a tangent line and a secant line that have the same vertex. So this point here, the two lines creating this angle, their vertex is at this point of tangency for the tangent line B. Point on the circle is what it has to be. Okay, so the arc that is between these two sides of this angle ABC is the blue arc. That's the intercepted arc. And what I need to take away from this theorem is that the angle created here is going to be half of whatever the measure of this intercepted arc is. So if this intercepted arc is 100 degrees, then the actual angle at ABC is going to be 50 degrees because it's going to be half of the intercepted arc, as you can see over here. So use that idea. We want to find the measure of EFH. So I'm wanting to find the measure of EFH. That's that entire angle there. What I know right now is that between these two sides, FE and FH, is an arc, FH, change the colors here, this arc right here, that measures 130 degrees. So what I know is that angle EFH has to be half of that 130 degrees, or 65 degrees. So it's fairly straightforward calculation. Now I want to find the measure of arc GF. So arc GF, I'm talking about going all the way around here, like so. Now in doing that, what I'm going to first do is realize that the measure of angle G, I want to mark angle G here that we're talking about because I see there's two angles at G. So this is the angle I'm talking about, the red one here. The measure of angle G is going to be half of the arc GF here. So, using that idea, I know that measure of angle G, because this other angle here is 122 degrees, I can just take 180 because I have a straight line and subtract the 122 to get that particular angle, and that's going to equal half of the arc GF. So what that's given me is 58 degrees is half of the measure of arc GF, and to get rid of that half, using my fraction rules, I'm just going to multiply by the reciprocal. The reciprocal of 1/2 is 2. So 2 times 58 gives me 116 degrees for the measure of that arc. Okay, now this theorem, you can see that the vertex, I have two chords, and they could be secants as well. They could be going through the circle. It wouldn't matter. But I have two chords in this picture. And the two chords intersect inside the circle. So I have a vertex in the interior. And what happens is the angle here, angle 1, is going to end up being half of the two intercepted arcs summed. Because I know that angle 1 has to be the same as this angle over here, because they're vertical angles. So the two arcs that they intercept, angle 1 intercepts arc AB, and this vertical angle with angle 1 intercepts arc CD. Basically, angle 1 is going to be the average of those two arcs. So add those two arcs together, divide by 2. And that's going to be the measure of your angle. So let's use that idea here. I want to find the measure of the measure of angle AEB. AEB is this angle right here. So what I notice is, of course, that's going to be the same as this angle, and the arcs that are being intercepted arc AB and arc DC. Those are the two arcs that are being intercepted. Well, I see that those are 139 degrees and 113 degrees. So I'm going to add those two together, divide by 2, and that's going to be the measure of my angle. So I'm taking half of 252 degrees. 126 is my total for the measure of angle AEB. So this one I'm just taking an average of the two intercepted arcs. Now I want to find the measure of RNM. You need to make sure that you pay close attention to the angle they're asking us for. RNM is this angle right here. So the information that I actually have is concerning completely different angles. I can solve for MNQ very easily because I have the 91, that intercepted arc, and the 225, the other intercepted arc. So I can just say that the measure of angle MNQ is add these two together and divide by 2. So I'll add the 91, the 225, divide by 2. Getting that is going to give me 158. Well, the trick then is, because what I have here is a straight line in RQ, straight as I can draw it, in RQ, what I have is these two angles have to add up to 180 degrees. Well, I just found out that MNQ is 158, so I can find the measure of angle RNM by subtracting 158 from 180 degrees. So that tells me that the measure of my angle is 22 degrees that I was looking for. So that's an indirect way of finding RNM, by finding actually a different angle and then using the fact that it's supplementary. Okay, this is a big picture to look at, but I want to make sure that you just kind of take it for what it is. Basically, if you have a point outside a circle, so in the first case C, in the second case F, and in the third case L, and it has two lines coming from that point, and both lines touch the circle, I don't care where. As you see, in this case, this line goes through, but this line is tangent. CA is a secant, CD is a tangent. In the second case, both lines are tangents, and in the third case, both lines are secant. So it doesn't matter, they just have to touch. It doesn't matter whether one's a secant and one's a tangent, they just both have to touch the circle. If they do, then all I do is take half of the difference between the two intercepted arcs. Now let's take a close look at those arcs so we understand what we're subtracting. So in the red one here on the left, I am going to show the two intercepted arcs. This goes through here, and it's intercepting arc BD and arc AD. Now, between those two arcs, AD is obviously the bigger arc. BD is the smaller arc. So I'm going to take the bigger arc minus the smaller arc, and then I'm going to take half of that value. So the measure of arc AD minus the measure of arc BD, and then cut that in half. Same idea for the one here with the two tangents. It's just that the two arcs are going to be the whole circle when it's all said and done. I'm going to have a major arc, EHG, so going all the way around here, and I'm going to subtract from it minor arc, EG. So I'm going to have the entire parts of the circle that I'm going to be subtracting and then cutting in half. And then for the last one, it's just going to be two smaller parts, JN, and then I'm going to subtract arc KM. Okay? And in all cases, once I take that difference, then I take half of that value. So let's use that here. I'm trying to find the measure of angle X. It's a angle outside the circle, so I'm going to subtract the bigger intercepted arc 87 minus the smaller intercepted arc 7, and then I'm going to cut that in half. Well, 87 minus 7 is 80, and half of that's 40, so it's a straightforward calculation. So I get 40 degrees for the measure of angle X. Same idea here. X is an angle outside the circle. The two intercepted arcs are the 200 degrees for arc AD and the 74 degrees for arc BD. So I'll subtract those two. 200 minus 74 giving me 126, and then I'm going to take half of that 126, which is going to be 63 degrees. Okay? So again, you're subtracting in this case and then taking half. Alright, now take that same idea, except in this case, instead of having you find the angle, I'm giving you the angle and I'm asking you to find one of the arcs. So my setup is still the same. This angle outside is equal to 1/2 the difference between these two arcs, so the 83 minus x. Here you got to be really careful and understand that idea of which arc is bigger, because it would give you a completely different answer if you say x minus 83 versus the correct one, which is 83 minus x. So you need to do the bigger arc minus the smaller arc. So my setup is the measure of angle L, the 25 degrees, equals 1/2 the measure of arc JN, the 83 degrees, minus the measure of arc KN, x degrees. So plugging those in, this is what we see. Now remember, when solving for a variable, we do PEMDAS, or please excuse my dear Aunt Sally, in reverse, meaning I'm going to take care of parentheses last. So the first thing I'm going to get rid of is the 1/2 by multiplying by the reciprocal, 2. So I'm going to multiply both sides by 2. It's going to give me 50 equals 83 minus x. Now what I'm going to do is 2 steps here. I'm going to subtract 83 from both sides, which is going to give me negative 33 equals negative x. So I'm just going to multiply both sides by -1, and then I'm going to have x as a positive 33. Okay. So 33 degrees for the measure of arc KM. Alright, now you can pause the video here. This chart is just a quick reference for you, kind of get your mind wrapped around the different rules that we've talked about. So when your vertex is on the circle, so in the first case here we have an inscribed angle, in the second case it's where I have the tangent and the secant meeting at that point on the circle. Both of those have the same formula, it's just half of their intercepted arcs. When my vertex angle is inside the circle, so the two lines, the two secant lines are intersecting on the interior, then that's where I take half the sum of the intercepted arcs. So I'm going to take the average. I'm going to add the two intercepted arcs, cut it in half. And then when my vertex is on the outside of the circle, as in this third case here, whether it's a tangent and a secant, or two secants, or two tangents, then that's where I'm going to be subtracting the two intercepted arcs and cutting that in half. So my rule applies consistently based on where the vertex angle is. So you can use this chart to kind of help you keep that straight. So pause the video if you need a little time on that. Okay, and we're approaching the end here. 2 slides left. So what we have is we want to find the measure of arc YZ. So arc YZ I'm talking about is right here. It's coming all the way around to here. I want to find the measure of that arc. Well, what would help me is if I knew the measure of arc UY, because I already have this angle that's outside the circle, 49, so I know that 49 is equal to 1/2 the measure of arc YZ minus the measure of arc UY, using our previous theorem we just talked about. So if I could find a way to get that arc, it would help me. So what I'm going to do is realize, first thing, that the measure of angle XVY, this angle right here, is going to just be 180 minus 113, because I have a straight line right here. So those two angles are supplementary. So I can find that angle fairly easily. And then I can use the fact that this vertex is inside the circle. And so I'm going to use my rule that the two intercepted arcs, arc UY and arc WZ, that this angle at V here, XVY, is going to be the average of those two arcs. Okay? So my setup is that I have 134, there's kind of a step missing here, so let me explain this. We did the 180 minus 113. That gave us 67 degrees for the measure of angle XVY. So I have 67 degrees here. Do my best to write that so it doesn't look totally awful. Okay, so 67 degrees. And that's going to equal this 1/2 the measure of UY plus 68. Again, it's the average of these two intercepted arcs. Well, remember, like we said before, please excuse my dear Aunt Sally in reverse. I'm going to get rid of this 1/2 first by multiplying by 2. So when I multiply the 67 by 2, I get 134 degrees. So that's where the 134 is coming from. And now I've gotten rid of the 1/2 on this side. So it's just the measure of arc UY plus 68. So now it's just a matter of subtracting 68 from both sides. And that tells me that the measure of arc UY, which is again this arc right here, and let me in fact change the color on that so we're really clear on this. This arc right here is 66 degrees. Well, the 49 out here is going to be 1/2 of the difference between YZ, what I'm actually looking for, and UY, which I just found to be 66 degrees. So my setup now is to just subtract those two numbers and take half of it. So YZ, the measure of arc YZ minus the measure of arc UY. Remember, we found UY to be 66 degrees, and we already know that the measure of angle X is 49 degrees, so we're just plugging those values in. I'm going to get rid of that 1/2 again by multiplying both sides by 2. So I'm going to have 98 equals the measure of arc YZ minus 66. Add 66, and the measure of arc YZ is 164 degrees. Okay, so we've reached the end of this lesson. I know it was a long one, 2 lessons in all here, so covering sections 10.3 and 10.4 out of your text. Thanks for following along. Have a great day.